All right, today we are cracking open one of the biggest cold cases in all of physics, Einstein's cosmological constant. We're talking about a mystery that's been haunting scientists for a century, all centered on a number so wildly wrong it's been called the worst prediction ever made. But what if the solution has been hiding in plain sight this whole time? Not in some exotic new form of energy, but in the actual, literal shape of our universe.
So, this whole story kicks off right here with what Albert Einstein himself called his biggest blunder. See, he put this little fudge factor into his equations for general relativity, this cosmological constant called lambda, just to make the universe hold still, to keep it static. But then, when astronomers discovered, whoops, the universe is actually expanding, he scrapped it, called it a mistake, and moved on.
But here's the kicker. What if he was right all along? Just for reasons that were totally impossible for anyone to grasp back then. That's the huge question at the heart of this explainer, as we follow a trail of clues to a solution that is, you'll see, just stunningly simple. Okay, let's get into the weeds here. Decades after Einstein gave up on lambda, it came roaring back. Astronomers figured out that the universe's expansion isn't just happening, it's speeding up. And suddenly, lambda, now rebranded as dark energy, fit the observations perfectly. But this solved one problem only to create a new one that was way, way bigger. Here's the problem in a nutshell. Our best theory for how the universe works at the tiniest scales, quantum field theory, says that even totally empty space, a vacuum, should be just fizzing and bubbling with a colossal amount of energy. But when we actually point our telescopes out at the cosmos and measure this energy, the value we get is tiny. I mean, it's so close to zero, it's almost comical. Just how different are we talking? The gap between what theory predicts and what we see is a 1, followed by 122 zeros. Let that sink in. That is, without a doubt, the single biggest error in the entire history of science. For decades, physicists have been completely stumped, but this new theory suggests maybe everyone's just been looking in the wrong place. See, this new idea flips the whole script. It says the answer isn't some mysterious energy filling up all of space. Nope. Instead, the cosmological constant is a direct result of the fundamental shape of our universe. The first clue is a pretty peculiar geometric object you might have played with before. Meet the Mobius strip. It's this wonderfully strange surface that only has one side and one edge. Imagine you're a tiny ant walking along its center line. After one full lap, you'd get back to your starting point, but you'd be upside down. There is no other side to be on. To get back to being right side up, you have to go around a second time. And hey, you can make one of these right now. Seriously, just grab a strip of paper, give one end a single half twist, and then tape the ends together. That's it. This simple, twisted little loop is the first key piece of evidence we need to solve our cosmic mystery. So here's how this theory puts all the pieces together. It imagines our 3D universe as what's called a three-sphere. The easiest way to picture that is as the 3D surface of a 4D ball. Now, the key part is that our 2D Mobius strip lives inside this space, and its one single edge forms this gigantic circle that stretches across the entire cosmos. Okay, so you're probably wondering, how on earth can a shape, just a simple twist in geometry, create a physical constant? Well, the best way to wrap your head around it is to think about music. The shape of a guitar string, right? Its length and tension determine the specific notes it can play. This theory says the universe works pretty much the same way. You see, in physics, these notes are called eigenvalues. They're just the natural resonant frequencies that any system is allowed to have. The specific shape of the system is what decides its unique set of possible notes. And that leads us right to the main question. If our universe has this particular shape, this Mobius-like topology, then what is its lowest possible note? What is its fundamental frequency? Okay, so this is the absolute crucial point. That half twist in the geometry creates a special rule for any wave or field traveling along it. To get back where it started, the wave has to be anti-periodic, which is just a fancy way of saying it has to flip upside down or flip its sign after one lap. And because of that rule, a flat line at zero is simply not allowed. It's forbidden. The lowest possible note, its ground state, has to be some non-zero value, a value that's directly tied to the size of the universe. And here's why it's a constant. This fundamental note isn't just anywhere. It sits right at the very peak of its own wave, a spot we call the antinode. At that one specific point, the slope is zero. It's a point of perfect balance, and it's topologically protected, meaning the geometry locks it in place.
It can't change. It can't evolve. It has to be a constant. This is where a true cosmological constant comes from. All right, we are on the home stretch. We have a value, a note that's calculated on a 2D surface. But you and I, we live in a 3D universe, so we need a way to translate our 2D blueprint into our 3D reality. So on that 2D Mobius surface, the theory calculates the value of this fundamental note, our lambda, to be 2 divided by the radius of the universe squared. That factor of 2, by the way, is there because we're measuring the wave at its peak intensity, at that antinode. So how do we make that jump from 2D to 3D? Well, luckily for us, some brilliant mathematicians back in the 19th century gave us the perfect tool for the job, the Gauss-Codazzi equations. You can just think of them as a universal translator that tells you exactly how the curvature of a surface relates to the curvature of the bigger space it's sitting in. And here's the beautiful part. When you apply these equations to a surface embedded in a universe like ours, under the simplest conditions, a really clean, elegant conversion factor just pops right out of the math. 3/2. This is it. This is the final key that unlocks the whole thing. We have all the clues now. We've got the shape, we have the fundamental note that shape creates, and we have the conversion factor to get us from the 2D blueprint to our 3D universe. It is time to put it all together and finally solve this case. And the final calculation is it's just beautiful. Look at this. We start with a value from our 2D Mobius surface, which is 2/r². We then multiply it by our 2D to 3D conversion factor, 3/2. And, well, look what happens. The 2's just cancel right out. And what are we left with? An unbelievably simple and elegant result. The cosmological constant, lambda, is nothing more than 3 divided by the radius of the universe squared. That's it. No mysterious dark energy, no quantum foam, just pure, clean geometry. But the ultimate question is, does the number actually work? Well, just look at this comparison. Here's the prediction from pure geometry right next to the actual value measured by our best astronomical data. The agreement is absolutely stunning. It matches what we observed to within about 2%. And that infamous 10 to the power of -122, it's not a mistake, it's the signature of the universe's geometry. And this brings our story right back to the beginning. Einstein didn't make a blunder. His only real mistake was losing faith in his own idea and taking geometry out of the equation. The cosmological constant wasn't an error. It was a glimpse of a deep truth about space-time that took us a full 100 years to finally understand. And so that leaves us with one last, really mind-bending thought to chew on. What if the deepest secrets of our cosmos aren't hidden away in exotic new particles or mysterious forces, but are written into its very fabric, its shape, its topology, a cosmic note playing out for all of eternity?